SwayamPrabha. Digital India. Educated India.
Today we continue our discussion on basic follower motions. In the last lecture, we have already discussed the simplest type of follower motion, which we called uniform motion. We also explained the difficulty associated with such simple motion, that is of infinite acceleration and deceleration of the follower at the beginning and end of the rise. Today first we take up a second type of motion, which is known as simple harmonic motion. In short, we call it SHM, that is simple harmonic motion. During this type of motion, the displacement of the follower y can be expressed as L by 2 into 1 minus cosine pi theta divided by theta Ri, where L is the lift of the cam, y is the displacement of the follower. For cam rotation angle theta, y is given by this, where theta Ri is the total cam rotation during the rise period. This expression is valid so long theta lies between 0 and theta Ri. In this discussion and all subsequent discussion, we will only discuss the rise phase of the follower. Now let us see, for this type of simple harmonic motion, what are the velocities and acceleration of the follower. As we know, velocity, which is given by dy dt, can be written as dy d theta divided by d theta dt. And d theta dt is nothing but the angular velocity of the cam, which is constant, we assume. So this is the constant angular velocity of the cam. So dy dt, that is the velocity of the follower, can be written as omega, the constant angular velocity of the cam, into dy d theta. For this expression of y, if we take dy d theta, we can easily see this turns out to be omega into L by 2 into pi by theta Ri into sine pi theta by theta Ri. So this is the expression for the velocity of the follower, and as we see, because of the sine term, it can never be beyond the range -1 to +1. So velocity is never going to be infinity. Similarly, if we look for the acceleration of the follower, that is the second derivative of y, d2y dt2, that we can get as omega squared into d2y d theta squared. Now if this is the expression for y, we differentiate it twice, what we get is L by 2 into, this gives me pi squared theta Ri squared into cosine pi theta by theta Ri. So again, as we see that the acceleration, because of this cosine term, can vary only between -1 to +1, the acceleration always remains finite. So, this avoids the difficulty of the uniform motion, where we found that the acceleration goes to infinity at the beginning of the rise and again goes to minus infinity at the end of the rise. Here it always remains finite. But if we look for the third derivative, that is the jerk, what we find, okay, let me talk about the acceleration a little bit more. We can see at theta equal to 0, that is at the beginning of the rise, acceleration, let me call it a, and this is the velocity of the follower, this is the acceleration of the follower. At theta equal to 0, we are getting acceleration is omega squared L by 2 into pi squared by theta Ri squared. So, it starts with an acceleration at theta equal to 0. That means at the during the end of the cycle, this is the starting point, and now it starts, it's here every derivative is 0, acceleration is 0 during this dual period, but as the rise starts with a value of the acceleration. So, the third derivative goes to infinity. The jerk, which is called the third derivative, jerk of the follower, that is the rate of change of acceleration, which is d3y dt3. Here d2y dt2 is 0, and it starts with a finite value of d2y dt2 at theta equal to 0. So, at the beginning of the rise, jerk tends to infinity. So, at theta equal to 0, rate of change of acceleration is very high. And at the same problem will happen when theta is theta Ri. When theta is theta Ri, this becomes cos pi, which is minus 1. So, again it has some negative acceleration at theta equal to theta Ri at the end of the rise. But at the end of the rise, again all derivative goes to 0. So, there is a huge amount of change of acceleration, rate of change of acceleration. So, again the jerk goes to a very high value. Now, let me see how we can construct the displacement diagram for this particular type of motion, which we call simple harmonic motion, because this displacement diagram drawing will be necessary if we follow a graphical method of cam profile synthesis, whereas this analytical expression is good enough for analytical method of cam synthesis. So, as before, we draw the displacement diagram. This is say theta equal to 0, and this is theta equal to theta Ri. This is the lift of the cam L. So, to express this equation geometrically, what we do, we draw a semicircle with L as diameter. We draw a semicircle with this lift of the cam as diameter. Our objective is to draw the displacement diagram for this value of theta between 0 to theta Ri. To do that, we divide this theta Ri into some equal number of divisions. I will explain it with 6 number of equal divisions. For more accuracy, you can take higher number of divisions, but the procedure remains the same. So, let me divide it into 6 equal parts. Say, I have divided this interval 0 to theta Ri in 6 equal parts. Then I also divide this semicircle into 6 equal parts. That means this is 30 degree, 60 degree, 90 degree, 120 degree, 150 degree and 180 degree. Now, if I call these as station points, I name them 1, 2, 3, 4, 5 and 6. Similarly, here also I name them 1, 2, 3, 4, 5, 6. Then I project these points horizontally and these points vertically. The corresponding points on this semicircle and on the theta axis and these points of intersection, if I join with a smooth curve, that gives me the displacement diagram corresponding to this equation. This can be very easily verified. As we see, this distance is L by 2, and if this is the value of theta, say, corresponding to the second station point, this is the value of theta 2, then this distance is L by 2 cosine theta. So, theta has been converted to pi. So, this angle is theta into pi by theta Ri. As theta goes to theta Ri, this angle, let me call it phi, goes to theta into pi by theta Ri. So, this distance is L by 2 minus this distance, which is L by 2 into cosine phi. So, y is becoming L by 2 minus L by 2 into cosine phi, which is nothing but as theta goes to theta Ri, phi goes to pi, and both starts at 0. As theta goes from 0 to theta Ri, phi goes from 0 to pi. So, when theta takes up the value of theta, phi takes up the value theta into pi by theta Ri. So, this geometrical construction reproduces this equation. So, this is the displacement diagram and this is the displacement equation for simple harmonic motion, which has one difficulty, as I showed, that the acceleration is finite here at the beginning of the rise and so at the end of the rise also, but after that the acceleration is 0, before that this acceleration is 0. So, there is a sudden change in the acceleration. The third type of basic follower motion that we will discuss is known as uniform accelerated motion or parabolic motion. In this parabolic motion, the half of the lift from the beginning of the rise up to the half of the lift, the follower moves with constant acceleration, and then for the rest half to reach the end of the rise, it moves with constant deceleration of the same magnitude. So, this is also known as uniform acceleration and deceleration. Uniform acceleration, constant acceleration for the first half of the rise, and the second half of the rise with the same value of deceleration. Now, if we remember the school mechanics, because the follower is starting with 0 velocity and also finishing the end of the rise with 0 velocity, then if the lift has to be covered in a given time, that is for a given value of theta Ri, if the lift L, given lift L has to be covered for a given value of theta Ri, which means for a given amount of time, because theta Ri is nothing but omega into t and omega is constant, then the maximum acceleration is minimum if it moves with constant acceleration. Any other variation of acceleration will make the maximum value of the acceleration during the cycle more. So, the maximum value of the acceleration will be minimum if it moves first half with constant acceleration and the second half with constant deceleration. Now, let us see, it is called parabolic motion because the displacement diagram is parabolic. Actually, there are two parabolas. Let us see how. As you remember, with constant acceleration, the motion is starting with 0 velocity will be proportional to square of the time. S equal to ut plus half at squared. If a is the acceleration, u is 0, initial velocity is 0 at the beginning of the rise, so the follower movement will be half a t squared. And t is nothing but theta, so I can write y as c theta squared. And this takes place so long theta is theta Ri by 2. The value of the constant c can be easily found out if we remember that at the half of the value of theta Ri, that is at the half of the rise, y is L by 2. It attains half of the lift when theta is theta Ri by 2. So that gives me the value of c as 2L divided by theta Ri squared. This is 4, so 2 cancels, this 2 goes there, 2L by theta Ri squared. So the expression for this uniform parabolic motion during this range of theta from 0 to theta Ri by 2, y is given by 2L into theta by theta Ri by 2 whole square. Theta divided by theta Ri whole square. This expression is up to this. For the second half, that is when theta lies between theta Ri by 2 to theta Ri. For the second half, when it goes with constant deceleration, we can easily write the expression of y as follows. If we draw the displacement diagram y, we have seen theta Ri by 2, this is theta Ri, this is L by 2 and this is L. So this first half of the rise, we have got this parabola. For the second half, when it goes with constant deceleration and again gets the velocity 0 here. So we draw the parabola from here at the other end, exactly the same parabola up to this point. So we have got the equation for this as this. We have to only write the equation for this. And this parabola is same as this parabola. So what is this? This distance is nothing but L minus y. And what is this? Which is equivalent to theta here, but here as I see, this is nothing but theta Ri minus theta. So we can write L minus y instead of y, then the constant remains the same, and for theta I write theta Ri minus theta, so that gives me 1 minus theta by theta Ri whole squared. So that gives me y equal to L into 1 minus 2 into 1 minus theta by theta Ri whole square. So this is the expression for the second half of the displacement diagram, and this is the expression for the first half of the displacement diagram. Next we shall discuss how do I draw this parabola graphically, because we may need to draw the displacement diagram graphically in case of graphical synthesis of the cam profile. These are the analytical expressions. Of course, we can take the values of theta and y and plot this graph, but there is a simple way of drawing a parabola which you must have learnt in your drawing course, but let me just recapitulate it. Let me now explain drawing of this parabola graphically. for the parabolic motion. I shall explain it only for one of the parabola, because the other parabola can be drawn from the other end, as I explained for the analytical expression. So this is 0, this is theta Ri by 2. So I have to draw a curve that the theta Ri by 2, it goes up to L by 2. And I have to draw this intervening parabola. To do that, we just divide this 0 to theta Ri by 2 in some number of equal parts. Let us say 3 parts. I am explaining it with the help of 3 parts. 1, 2 and 3. So this is 1, this is 2 and this is 3. And as we said, the y varies as square of the angle theta. So we have to divide this interval as the square of 1, 2 and 3, that is 1, 4 and 9. So I draw a line through this point and make equal divisions 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are all equal divisions. So I have to divide this in the ratio of 1 is to 4 is to 9. So I draw it line. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this line has to be divided in the ratio of 1 is to 4 is to 9. So this total is 9. So I divide this, I draw a line parallel to this line from here and this line from here. So from here I project, from here I project, and from here I project, and I get the required parabola. And exactly the same way I can draw the other parabola. But the thing to note is that here it is going with positive constant acceleration, and now it goes with negative, same value of negative constant acceleration. So here the acceleration changes from plus f to minus f. So there again the jerk goes to very high value from plus f to minus f. And here from minus f to 0 at the end of the rise. So here again the jerk acceleration goes from minus f to 0 suddenly, so the jerk goes to plus infinity. And the same problem is here. The acceleration before the rise was 0 and suddenly it starts with constant acceleration, so the jerk goes to infinity. So these are the problems with the parabolic motion, but it has the advantage that to cover the same lift in a given time interval, that is given value of theta Ri, the maximum value of the acceleration is minimum for this. Here of course the maximum is constant, that is whatever f we have got. But for other motions the maximum value of the acceleration will be more. Now sometimes we also use modified parabolic motion. That means, for example, in the case of automobile valve, the valve has to open very fast. Similarly, the valve has to close very fast at the end of the return. During these two portions, I will use a larger value of acceleration and then follow with constant acceleration the rest of the path. That means the acceleration initially, if that is f1, and for the rest of the period the deceleration, that is the magnitude of the acceleration, is f2, then f1 is larger than f2. That way the valve will open very fast, then rest of the opening will be gradual with a lesser value of acceleration. And we can say f1 equal to say some constant into f2, and k is more than 1. This is the starting acceleration here and the rest of the deceleration there. In that case, it is very easy to show. If we are given the value of k, Then how to draw the displacement diagram or write the expressions? That is very simple. Suppose this is theta Ri. Then up to what angle of theta it will move with constant acceleration F1. That you can easily show that this should be theta Ri divided by 1 plus k. And with this, how much of the lift will be covered? If this is the lift, then the rise with constant acceleration F1, this will be L divided by 1 plus k. This is very easy to see. It starts with 0 velocity, attains some velocity v here, and then it decreases and again becomes 0 velocity here. So you can easily show that as you know, v equal to f1 t1 if this time interval is t1, and also v equal to f2 t2 where t2 is this time interval if this is t2 when we talk in terms of time. But theta and time are proportional. So you can see t2 by t1 is f1 by f2 is equal to k, and t1 plus t2 is the total time. So we can write, if this I call theta 2 and this I call theta 1, then theta 2 by theta 1, which is same as t2 by t1, is k. So theta 1 is total theta Ri divided by 1 plus k, because theta 2 is k theta 1. So theta 1 plus k theta 1 is theta Ri. Theta 1 plus theta 2, which is k theta 1, is theta Ri. So theta 1 I can easily solve for theta Ri by 1 plus k. Similarly here, the distance covered, if I call it S1, then v square you know is 2 f1 s1. Similarly from the other end, starting from 0 velocity, it is covering a distance s2 and reaching the velocity v. So this is twice f2 s2. So same way I can get s2 by s1 also k f1 by f2 is equal to k. And s1 plus s2 is the total lift. So this I call s1, and the rest of the lift I call s2, and as we see s2 by s1 is k and s1 plus s2 is L, so s1 turns out to be L by 1 plus k. So these are very simple things, you can do it yourself. This is called modified parabolic motion. There are two parabolas but not identical for a part of the rise and the rest of the rise. Next we shall discuss another type of basic follower motion. Next we discuss, as I said, another type of basic follower motion known as cycloidal motion. The word cycloid, you may know, it is the curve which is generated when a circular wheel rolls without slip on a flat surface. Suppose we talk of a circular wheel of say radius r is rolling over this flat surface, and if I look at the curve which is generated by any point of this wheel, for example say right now I concentrate this point which is in contact with the horizontal surface. Now as this wheel rolls, this point obviously will go up to 2r height and then again come down in one cycle of rotation. This is 2 pi rotation of the wheel, And this curve generated by this any point, for example this point P, this is called a cycloid. And let us see what is the expression for this cycloid. And for the cycloidal motion, the follower displacement y will be given by L into theta by theta Ri minus 1 by 2 pi sine 2 pi theta divided by theta Ri. Now this expression can be easily shown from this diagram. Suppose this is the lift L and that corresponds to theta rotation of the cam. This is the lift L and this corresponds to theta going from 0 to theta Ri, where theta is the cam rotation. And the wheel rotates from here to there by 2 pi. So wheel rotation, if I denote by phi, then phi can be written as corresponding to theta, it will be 2 pi by theta Ri into theta. When theta is 0, phi is 0. When theta is theta Ri, phi is 2 pi. Now, due to this rotation, let us say it is rotated by phi and the wheel has taken up this position. The wheel center has moved so much. And this point P has come here. So we have to find out what is this height. So if I call this center of the wheel as O, which has gone to O1, and the new point of contact is here, which is P1. And this point P has moved to this point, which I call, say, P prime. Now, what is the height of P prime? Can I express it in terms of theta? This is my y. Theta is nothing but represented by phi, and phi and theta are related by this. Theta is the cam rotation, phi is the rotation of this wheel. So this vertical radius OP has now become O prime P prime. And this rotation is phi. This rotation is phi. Now, because the wheel is rolling without slipping, I know this distance, sorry, this is not y, it is this which is y. This is the lift. So the displacement of the follower is measured in this direction. This is the lift of the follower. So the movement of the follower is given by this distance. From P, it has gone there, and what is the corresponding movement in the direction of the follower movement is this. This is y. Now, because the wheel is rolling without slipping, this arc length on the wheel is same as this distance. The distance covered by the center of the wheel or the distance covered on the road. This arc length is same as this. And what is this arc length? Arc length is, if radius of the wheel is r, then r into phi. And y is this minus this distance, which is r sin phi. So r sin phi. So this is y. R into phi minus sin phi. Now let us see what is r. By one complete rotation of this wheel, it has covered a distance L, so r is obviously L by 2 pi. And now let me put the value of phi in terms of theta, which is 2 pi theta by theta Ri minus sine 2 pi theta by theta Ri. And that gives me this expression for the cycloidal motion. 2 pi cancels, so it gives me L into theta by theta Ri, and this 2 pi I take inside, 1 by 2 pi sine 2 pi theta by theta Ri. So this is the expression for the cycloidal motion. Obviously it is valid in the range 0 to theta Ri. In this range, the displacement of the follower is expressed by this equation. Now we can study the velocity and acceleration of the follower for at the beginning and end of the rise. For example, if you remember, for the simple harmonic motion, the one difficulty was that the acceleration from 0 took up a constant value to some finite value at the beginning of the rise. So the jerk was very large. Now let me calculate the acceleration of the follower. So this is the expression for the cycloidal motion, which is valid for the entire rise period. If you remember, for one of the basic follower motion like simple harmonic motion, it started with a finite acceleration, which created a very large value of the jerk, infinite jerk. Let me see what kind of initial values the cycloidal motion creates. If you remember the velocity, I can write dy dt, which is omega times dy d theta. So what we get? Omega into L, differentiating this, we get 1 by theta Ri minus, if I differentiate this, 2 pi by theta Ri, 2 pi cancels with this, 1 by theta Ri into cosine 2 pi theta. So the velocity at the beginning and end of the rise, that is the theta equal to 0, velocity theta is 0, this is 1, this cancels, v is 0. At theta equal to theta Ri, so 2 pi theta by theta Ri. This is 2 pi by theta Ri, which this 2 pi has been cancelled from here, and cosine 2 pi theta by theta Ri. At theta equal to 0, velocity is 0. Now if we put theta equal to theta Ri, then again this is cosine 2 pi, which is 1, so again velocity is 0. So it starts with 0 velocity, which is desirable, and ends the rise, that is starts the dual also with 0 velocity, which is desirable. Now let me calculate the acceleration. Acceleration will be omega squared into the second derivative of y with respect to theta. So if I differentiate it twice, what we get? This does not give me anything, and this gives me 1 by 2 pi into 4 pi squared by theta Ri squared. You get it twice, and minus minus makes it plus, sine 2 pi theta by theta Ri. So this is the value of the acceleration for any value of theta. Now at theta equal to 0, again acceleration is 0, and at the end of the rise, the theta equal to theta Ri, again acceleration is 0. Theta equal to theta Ri, also acceleration is 0. As is found here, at both theta equal to 0, v is 0, and theta equal to theta Ri, v is 0. So cycloidal motion has this advantage that at the beginning and end of the rise, not only the velocity is 0, acceleration is also 0. So that gives a little smoother motion than as compared to the harmonic motion. Next I will show how to draw this displacement diagram corresponding to this cycloidal motion. Now that we know that the expression for the cycloidal motion, the follower displacement expression we have just now shown is L into theta by theta Ri minus 1 by 2 pi into sine 2 pi theta by theta Ri. Now I will explain how to draw the displacement diagram corresponding to this expression. So this is 0 and this is theta Ri, and this is the lift L. As we have shown that it is really rolling a circle of radius r equal to L upon 2 pi, such that one full rotation of this wheel will bring the wheel to the end of the lift. This is the lift. One full rotation of this wheel will bring the wheel to the end of the lift. So to draw this curve, what we do, we draw the same wheel here of radius L by 2 pi, and then divide this rise period into equal number of divisions. So let us say 6 divisions. And mark these station points 1, 2, 3, 4, 5 and 6. These are 6 equal divisions. This circle we also divide into 6 equal divisions. This is 0, 1, 2, 3, 4, 5, 60, 120, 180, 240, 300. So we call it 0, 1, 2, 3, 4, 5. Now we draw this diagonal then this straight line represents this part of the curve, L into theta by theta Ri, because as theta goes to 0 to Ri, y goes to L, and linearly, so this straight line represents this portion which is a straight line. Now I have to subtract this. So what I do, I project these points onto this vertical diameter. This I call, say, 1 prime, 2 prime, and this is 4 prime, 5 prime, and the center of the wheel which takes 0 and 3. So from this I draw a line which is parallel to this. And from this point again I draw a line which is these two lines are parallel to this diagonal. Now from these corresponding station points this line was from 1 prime 2 prime, which was the projection of this 1 and 2 on the vertical diameter. So from here I draw the vertical lines to intersect this line corresponding to 1 prime 2 prime. And from here I draw the line to intersect this line which is drawn to the center, which you can call 0 prime and 3 prime. And this line, which is drawn from 4 prime and 5 prime, I intersect, draw these vertical lines. Now, through these points, if I join these 6 points, I get the desired cycloid. This curve represents this equation. It is very easy to see that this vertical height, which I am subtracting, is nothing but express this, because this rotation is 2 pi into theta by theta Ri, and radius is L by 2 pi, and this is the sine of that angle. The vertical height is nothing but the sine of that angle, which I have subtracted from this line, this vertical subtraction. So this is the cycloidal motion. If you remember, the cycloid is really this curve. This is the curve generated by a point on this wheel. So we have the expression. This is valid for 0 less than theta Ri, and this is the geometrical construction corresponding to this equation. Now that we have discussed all types of basic follower motions like uniform motion, simple harmonic motion, parabolic motion, or modified uniform motion, or modified parabolic motion, or cycloidal motion, we have seen there is one kind of difficulty, is that some derivatives of the follower displacement like velocity, acceleration, jerk, etc., may be very high at the beginning or end of the rise, or at some intermediate point during the follower movement. To avoid all this, what is sometimes done, we cannot avoid it totally. All higher order derivatives cannot be made 0, but some derivatives can be made 0 at both beginning and end of the rise by using what is known as advanced or polynomial Cam curves, and the corresponding cams are called polydyne cams. This advanced Cam curves, what we do, we write the displacement of the follower as a polynomial of theta, an algebraic expression using powers of theta. Say I write up to 5th order. I write up to C0, C1 theta, C2 theta squared, C3 theta cube, and so on up to the 5th order term. And these I leave as constants which are so set such that value or the derivative of y at theta equal to 0 and theta equal to theta Ri can be controlled. For example, what we need at theta equal to 0, y has definitely got to be 0, and we also want the velocity to be 0, which can be ensured by having dy d theta 0, and suppose we also want the acceleration to be 0, which can be ensured by having the second derivative of y with respect to theta to 0, which immediately tells you that C0, C1, C2 all have to be 0. Because if you put theta equal to 0 here, y0 gives me C0, 0. Similarly, if you take derivative, C1 stands at the first derivative. At theta equal to 0, all other term goes to 0, so C1 needs to go to 0. Similarly, from the acceleration, I will get C2 equal to 0. Now, at theta equal to theta Ri, at the end of the rise, I need y has got to be equal to the lift of the cam, that is L, but I want it to have 0 velocity and 0 acceleration. So C3, C4, C5 should be so chosen that these three conditions are fulfilled at theta equal to theta Ri. Y is L, but derivatives are 0. We can solve for the remaining three unknowns, namely C3, C4 and C5. This is a matter of simple algebra. You can do it easily, and you can solve for three linear equations you will get in C3, C4 and C5, and if you solve those, you will finally get the expression as y equal to L into 10 theta by theta Ri cubed minus 15 theta by theta Ri to the power 4 plus 6 into theta by theta Ri to the power 5. The coefficients 10 by theta Ri cubed and 15 by theta Ri 4 and 6 by theta Ri 5, you can solve for C3, C4 and C5 using these three conditions. As the third, fourth and fifth order terms are remaining, this is called a 3, 4, 5 curve. So this is what we call advanced CAM curve. There are other kinds of advanced CAM curves which we are not going to discuss in this course. Let me now summarize what we have done today. Today we have discussed all types of basic follower motions, namely simple harmonic motion, uniform or parabolic motion or uniform acceleration motion, and cycloidal motion. We have also touched upon a little bit about the polynomial expressions for the follower displacement. We have seen their analytical expressions and also how to construct the displacement diagram corresponding to these analytical expressions. Our next task will be that if y as a function of theta is either prescribed or given in the form of a displacement diagram, how to design the CAM profile or how to synthesize the curve of the CAM profile. That we will start in our next lecture.